Hello and welcome back to Calculus 2, section 6.7 on physics applications. We're going to now involve integrals in various physical applications. So first off, this is the last section of chapter 6. We have 3 sections left in chapter 7, and you guys are ready for the first exam at that point if you want one. So stick around next week to vote. So physics, also known as applied mathematics, right? We're going to take a look at few concepts. We already looked at kinematics in Calculus 1. We know that you have a position function. You can differentiate to get velocity function, to differentiate again to get acceleration function, differentiate again to get jerk. These are all physical concepts that you can measure in a lab and calculate with these calculus equations, and then match them and see that within the reasonable error with measurement, you actually have the same solution. Today, we are going to take a look at few concepts that would involve integrals. We are going to start with figuring out the mass of the object if you know the density. So mass is one of these things, properties of matter, that in some cases is difficult to explain because it doesn't depend on things that you generally get in touch with. The way I like to describe mass to easily understand it is quantification of physical existence. Okay, so it gives a number to physical objects, to stuff, which includes people as well. So your mass in terms of your body, so not your weight, your mass. Your mass is equal no matter where you measure it. See, your weight is different if you weigh yourself on Earth, if you weigh yourself in a moving elevator, if you weigh yourself on the moon. Your weight is different because the weight is the force which presses the scale, and the weight is mass times the gravity. So see, the mass is the part of the formula for weight. So when you are buying 3 pounds of bananas, you are actually you are paying for 3 pounds, and 3 pounds is actually the force. You're not paying for bananas. You are paying for the force with which bananas push the scale to tell you it's 3 pounds there. If you're buying 1 kilogram of bananas, then you're actually paying for bananas, because kilogram is the mass of bananas, which is a very funny concept. Anyway, so the mass doesn't depend on gravity, doesn't depend on your mood or anything. The mass is this constant and the mass would depend on the density of the object. So the denser the object for the same size, the object will be heavier in terms of the mass. So if you compare, there's that trick question going around, what's heavier, pound of feathers or pound of gold, right? And people that are not paying attention, they immediately go for gold because gold is heavy and feathers are not heavy. But I said 1 pound of gold and 1 pound of feathers. So I don't care that I need a truckload of feathers to make 1 pound and a little nugget of gold to make 1 pound. That doesn't matter. See, the trick is that feathers are not as dense as gold. So gold as a denser material is going to be very heavy. So now move to lead, move to uranium and plutonium and whatever else you want, right? So we are going to define a mass as integral of density function, because the density is the one that will give you mass at the end. The more dense objects, right, will be the heavier. That's my category. And then your category, less dense objects, right, so you're lighter. So we have the mass in a one-dimensional object. We're going to do this like this. So I'm just going to say mass, and I'm going to say that the mass is equal to the integral from A to B of rho of x dx. So this is our function, our formula, and I'm going to give you the legend on the side. M is mass, rho of x is density function. And very important aspect over here is this is one-dimensional object, 1D object. Now, we don't really have one-dimensional objects in existence. We don't have two-dimensional objects in existence. You know what the one-dimensional object is? Your number line. That's it. There's nothing else. What's a two-dimensional object? A triangle. Can you pick up a triangle? No, it's a drawing on a surface. Or a square or a circle. Right? The only things that you can pick up are third-dimensional. The entire world. You can see one-dimensional object because I am able to draw x-axis, and that just has length. And I am able to draw a triangle, which is a 2D object, and that's that. I can't pick up either of these. Because as soon as I pick them up, they have to have thickness to exist. None of these have thickness to exist. They're just drawings. So going from one dimension to two dimension to three dimension is what the world we live in has x, y, z, 3 dimensions. So everything that you have now is three-dimensional. Now, what I can do with this keyboard cover, right? This is keyboard for the surface, right? So this is a three-dimensional object because it has its length and the width, but it also has thickness. And the thickness of this would give it a third dimension. Yes, I understand it's like 2 millimeters or 3 millimeters, but it's still 3 millimeters of thickness. And if it's a 3 millimeters of thickness, that adds a third dimension, and this is a three-dimensional object that has length, width, and in this case, height. 3 millimeters of height. But for practical purpose, this 3 millimeter thickness in comparison to the length and the width of this keyboard is insignificant. So we can regard this as a two-dimensional object because the two dimensions that are in charge, right, are much bigger and stronger than the one dimension that it's the thickness, which is 3 millimeters. So you are talking about 3 millimeters against 10 centimeters. That's a lot of the orders of magnitude, 2 orders of magnitude difference, right? And same for the length. So can I regard to anything as a one-dimensional object? And the answer is yes. Take a long wire. It is a three-dimensional object. If you put an ant on the wire, it's going to go around the wire, right? So the ant would experience a two-dimensional surface because ants can only, right? They're so small that any surface is immediately 2D. Just everything is flat. That's why they go in a circle like this. But if you take a piece of wire and you put it under the magnifying glass, that piece of wire is going to, when magnified, going to look like a cylinder. It's going to look like the bottle or a Coke bottle or something, right? I mean, can. So if you enlarge it, you're going to see that it's a three-dimensional object. But then the two dimensions for that cross section of a circle are so small, 2 millimeters, 3 millimeters, and then you have the wire that is 6 feet long. You want to charge your cell phone across the room. Nice. So those two dimensions for the cross-section circle are completely overshadowed by the 6 feet length of the cable. So you can think of the cable as a one-dimensional object, even though you know it's a three-dimensional object, but the only one dimension that matters is the length. How many of you shopped on Amazon or whatever for a new cell phone charger with the cable, right? And you were considering not just the length of the cord, but you were also considering the cross section? No one, right? Of course, no one. Because you know that the cross section is going to be whatever it has to be, some engineer figured it out, all right? All you care about is the length of the cord. You care only about the single dimension, right? Which was the length of the cord, completely disregarding the hard work of engineer who said, well, we have to have this particular gauge for the wire, otherwise fire, right? So we can write this mass as a one-dimensional integral, and we have to limit it there today. And in Calculus 3, you are going to write the mass using double integral for two-dimensional objects and triple integral for three-dimensional objects. And you will use that to find the center of mass, so that when you know the mass of the object and you know the moments and stuff, you will be calculating that in Calc 3. You put the point where it goes and it will be perfectly balanced. It will stay. That's the center of mass. Now, generally, we don't care the center of mass of this because, right, but you definitely care about center of mass for third-dimensional objects like cars and planes and ships and things like this, because you don't really want those things to tip over. When the SUV craze started in the United States, whatever amount of years ago, they used to have commercials on the TV because people are dying left and right because they were driving SUVs the same way they drove regular cars. What is the problem of SUV? It's much taller, it's top heavy. Top heavy means your center of mass is higher. And if the center of mass is higher, it's easier to flip, right? It's harder to flip shorter person, right? Because they're closer to the ground. And taller person easier to flip because the mass is higher, right? Another thing would be the safest car in the galaxy, Tesla. No engine. It's not top heavy. Where's the stuff? The battery that sits underneath the driver, right? In the whole bottom of the car is the battery. And that's where the weight is. The car was so light when you take out the engine block. You know, the engine block is the solid piece of metal that's this big. Solid. That gives the car a lot of weight. And then the engineers have a lot of work to do to figure out to reduce that mass, right? But you can't, because you have to have a solid block, because what is happening inside? You squirt in dead plants and animals on one, and the oxygen, and then the spark ignites that, makes a little explosion and pushes the piston up, right? So that's what you do. When you have the gas-powered car, you are exploding dead plants and animals with oxygen, and that propels you at 27% efficiency. Nice. Awesome. What is Tesla, right? Just the battery that goes directly into the motor, 98% efficient, right? Low center of mass. So what they have a lot of weight to play with. Because if your car is more powerful than the gas-powered car, and it's much lighter, once you push the pedal, it's just going to spin and spin and not go anywhere, because there will be no traction, because the weight is the one that pushes the car down, that pushes the tires against the pavement to go. So they had to steal